coming up what's due on Sunday is the Chapter 4B questions and discussion. So Chapter 4B is all about types of reactions. So we talked about last class or last video, the synthesis combination reactions, we talked about decomposition reactions, single replacement, double replacement, and combustion. So if you're given an equation, a chemical equation, kind of like you see up on the board, you need to be able to identify what type of reaction it is. All right, but what we're going to look at today is the predicting products part. So sometimes you're only going to be given the reactant parts, so the things that are going in the flask, and you're going to have to predict what products will be made. So we're going to go through some examples of this, and you only are going to need to predict products for single replacement, double replacement, and combustion. So you won't have to predict them for synthesis or for decomposition. So when you're starting, it's best to identify the type. So we're going to still do the same steps. We're going to identify the type. We're going to go ahead and predict the products. We're going to balance the equation. We're going to do it all. So we'll start with the type, because figuring out the type of reaction is going to help us predict the products. So looking at this first example, we have an element by itself reacting with a compound. So since these are our only choices, these three, that will help us narrow it down. So for combustion reactions are always a hydrocarbon reacting with oxygen. So it's definitely not a combustion. Double replacement, that's two compounds reacting and switching partners. And we don't have two compounds, we have one compound and one element by itself. So that narrows it down and tells us it's single replacement, because single replacement has an element by itself, switching places with a compound. So the type is single. And how do you figure out what the products are going to be? Well, what we're going to write down here is we're going to write the charges of each of these elements when they're in a compound, because that's going to help us figure out who's switching with who. So when I look at iron, when iron's in its elemental form, like here, its charge is actually 0, it's neutral. But we want to look and write down here what would its charge be if it was in a compound. Okay, now iron is a transition metal, so it does have multiple variable charges. It can be a +2 or a +3, but what's important is that you know it's a plus, because the cations are going to switch with the cations. So let's look at what I mean by that. Hydrogen and chlorine. These two are together in a compound, so they do have charges. We need to figure out what those charges are. Well, chlorine is always a -1. It's a halogen. Hydrogen is a +1 in this case, because we need this compound to be neutral. So if the chlorine is a -1, the hydrogen has to be a +1. So knowing these charges are going to help us figure out what the products are, because the cation is always going to switch with the cation. So when I look to see who the new partners are on the product side, I'm going to want to put a positive with a negative, because opposites attract. So I'm not going to see the iron and the hydrogen form a bond, because they're both positively charged and they're going to repel each other. So what I'm going to see is the iron with the chlorine on the product side. That's one of my products, once I do the crisscross method. So the reason I'm writing the charges is, first of all, to see who's going to go with who, but also, notice up here, I wrote new partners equals new subscripts. So not only do I need to figure out who goes with who, I need to figure out what this looks like when it's neutral. What's this compound going to look like? So I have Fe2Cl. So what is that going to look like in an actual compound? Well, we did this in the last chapter. You can do the crisscross method, where this 2 becomes a subscript on the chlorine, and this 1 becomes a subscript on the iron. Or you can see, well, I need to add another chlorine anion so that I have a -2 charge to cancel out the +2 charge. Either way, what you're going to get is Fe1, you just need one of them, and then Cl2. Leave a little space there for when we balance. So FeCl2. All right, so that's one of the products. Now notice we still have hydrogen that hasn't done anything, so we need to include hydrogen. And when I include hydrogen on the product side, I'm not just going to write H, okay? Because remember, hydrogen was one of those 7 elements on the periodic table when we made that number 7. I highlighted it in green. There's always a diatomic in nature. So what that means is hydrogen's never just going to hang out as an only atom. It's always going to be H2. The other ones we looked at, as a reminder, were nitrogen. So nitrogen's always N2. Oxygen will always be O2. And then all the halogens, fluorine, chlorine, bromine, iodine. So those always exist as diatomics. So that's how I know that's H2 and not H. It's just the rule that hydrogen's always a diatomic when it's by itself. So this is how I'm going to predict the products. But once I have the products, I already know the type is single, I need to balance. So to balance the reaction, we went through the steps last time where we made a list of all the elements and made sure it was the same on both sides. So I'm going to do a shorthand version of that. And what I mean by that is I'm just going to look at what they have directly. So there's one iron, so that's good. I have one chlorine here, or one hydrogen here, sorry, 2 hydrogens there. So that means I need 2 on this side. So if I put a 2 here, now I have 2 hydrogens, 2 hydrogens. So that's balanced. The last element I need to look at is my chlorines. 2 chlorines because of that coefficient of 2. And then the subscript here of 2 tells me there's 2 chlorines on that side as well. So that's balanced. The nice thing about single replacement reactions is they're usually pretty easy to balance. All right, so we've done all the steps on that one. We did the type, we predicted the products, and then balanced. So now we're going to try another one. I'm going to have to go ahead and erase this so that I have room. So notice it only gave me the reactants because I have to predict the products. And since we're only predicting products for these 3 types, that narrows it down for me when I'm trying to figure out what type it is. So looking at this one, we start by identifying the type. So is it single, double, or combustion? Any guesses? It's double, because double is 2 compounds reacting together. So I have calcium bromide, which is a compound because there's 2 or more elements combined, and I have silver nitrate, also 2 or more elements combined. So this would be double. And that's going to help me figure out what my products are. So what we're going to have is we're going to have partner switching. And if you remember, you can also use that AB plus CD pneumatic that I gave you when we talked about the types of reactions. Because what happens is A is going to be with D on this side, and then C is going to be with B. So this could help you figure out who the new partners are as well. But since you have to know the charges anyway, because new partners equals new subscripts, we're going to do the same steps that we did with the single replacement reaction, and we're going to write all the elements and what their charges would be. Okay, so I'm going to take this calcium bromide here, and I'm going to write just the elements themselves and what their charges are. And to figure out the charges, we're using the periodic table. Okay, so calcium. Calcium's an alkaline earth metal. It's in group 2. This is something we learned in chapter 3. This is the reason we did all this, is to lead us up to here. So since it's in group 2, it's going to form a +2. What is bromine's charge when it's an ion? halogen, -1. All halogens are -1. They're one away from being a noble gas. Now for silver and the nitrate. So we've done ones like this before. It's a transition metal, so this is our question mark, right? We don't know what it is. But we can figure out what NO3 is by looking at our polyatomic table. So when I look up NO3, it's nitrate. And correct me if I'm wrong, but I believe it's a -1. So to figure out silver, we use this charge of -1 to help us figure that out. Since this compound has to be neutral as a whole, what is silver going to have to be? We got a -1 here, so to cancel it out, we need a +1. So now it would be neutral. Notice when I wrote these down here, like there are 2 bromines, but I'm not worried about how many bromines. Okay, I'm just worried about what the charge is on bromine. Because I'm not bringing this 2 over here. Because I'm going to have new partners, so I'm using the charges to figure out what my new subscripts are going to be. Okay, so now that we know the charges, we can figure out who needs to switch with who. Because what we're going to have is we're going to have the positive cation switch partners and become partners with the negative in the other group, because opposites attract. So the calcium, which is A, is going to partner up with NO3D. That's how we get A and D together. Okay? And the reason they partner up is because they have opposite charges. So when I write them over here, I'm just going to write the charges first, and then I'll figure out what the actual compound looks like in a minute. So I have Ca2+, and it's now going to be partnered with my NO3, which has a -1 charge. Okay, my A and my D. My next compound then is going to be what's left over. And what I have left is the silver and the bromine. So silver and bromine are going to partner up. When I write them, I'm going to put the silver first because the cation always comes first. So I'm not going to write Br and then Ag. It's always going to be cation first and then the anion. So I'm writing their charges so that I can use those to figure out what the actual compound is going to look like. So now, AgBr, that's my C and my B, right? We have C and B together. So now we're going to use the charges to figure out what it looks like. So we're doing that crisscross method from chapter 3. So this 2 is going to become a subscript on the NO3, and this 1 is going to be the subscript on the calcium. So that means I'm going to need 1 calcium, so Ca, just with the 1, you don't have to write it. And then the NO3, I'm going to have 2 of them. So when I write the NO3 and I have 2 of them, it's a polyatomic, so what do I have to make sure to do? Parentheses. So parentheses and then the 2. Otherwise, it's going to look like I have 32 oxygens. So this is one of my new products. Notice there's different subscripts than there are over here because we have new partners. I'm going to put a space for when we balance, then I'll do a space, and then let's figure out what this guy's going to look like. Well, looking at its charges, it's already neutral, so I just need 1 of each. So silver, bromine. So we have identified the type, we have predicted the products. Now let's balance the equation, and notice in green up here, if it's a double replacement, which we said it was, we're going to predict if a solid formed using our solubility tables. Okay? The driving force for most double replacement reactions is that a solid or a precipitate formed. So let's do our balancing first. I'm going to erase this bottom portion. And you can make the list if you want to, or you can just compare them using the equation itself. So I have 1 calcium here, I have 1 calcium here. So those are balanced. Looking at my bromines, I have 2. Over here, I only have 1. So I need 2 bromines on the product side. So what number am I going to put as that coefficient? A 2. So now I have 2 bromines. So my bromines are balanced. Looking at the silvers, on the reactant side I have just 1. On the product side, how many do I have now? 2, because I put that coefficient of 2, so I have 2 silvers as well. So I need to make 2 over here. So what coefficient do I have to put? A 2, so I have 2 silvers, 2 silvers. So the silvers are now balanced. My NO3s, I have 2 nitrates because of that coefficient of 2. On the product side, the subscript of 2 tells me I have 2 nitrates. So the nitrates are balanced as well. And if you want to write it out, by all means go ahead and do that and make the list and check it to make sure that everything is balanced. And you'll see that it is the same. Oops, I did bromine of 1. That's wrong, that's 2. But a lot of times with single and double, since they are fairly easy to balance, it's not always necessary to write it all out, especially once you've practiced balancing quite a bit. All right, so last step, let's figure out if a solid formed. So whenever they ask this question, which is the solid in this reaction, the nice thing is the reactants are never going to be the solids. Notice I have an AQ by both of these. So AQ meant aqueous. So how do I know they're aqueous? Well, because they're both ionic compounds, and when we react them together, we dissolve them in water. They're solids initially, but we dissolve them in water to make aqueous solutions because that way they break apart to their ions in solution. And that's going to help them react faster. So that's what we do to help the reaction just move faster. So the reactants are usually almost always aqueous solutions when we're doing double replacement. And we just have to look at the 2 products and figure out which of the products. So we're only looking at these 2. So let's start by looking at our calcium nitrate. Does everyone have their solubility tables? We only have 1 left. You have 1, Teresa?
I don't think so.
Oh. You don't have 1 either, do you, Tyler?
Nope.
I had a lab yesterday and everybody grabbed an extra one. I don't have any more. But I'll write up on the board how to tell if it's
Oh, I have 1.
soluble or not. Thank you.
Thank you.
So calcium nitrate's the first one we're going to look at. So how you figure this out is you either find the calcium ion on your solubility table or the NO3 ion. Now, if you find the NO3 ion, I think it's in the 2nd row. Is that correct?
Yes.
NO3 minus?
7,
So it says it's soluble, right? It's under the soluble column. You follow it over, and are there any exceptions? So NO3, it says it's under the soluble heading, and for exceptions, are there any exceptions? Does it say none? It says none? Is that correct? Okay. So none for exceptions. So what this means is soluble means dissolved. So it means it's an aqueous solution. And since there's no exceptions, that means no matter what NO3 is attached to, it's going to be an aqueous solution all the time. Doesn't matter who its partner is. So what this tells me is that calcium nitrate is AQ, so that did not form a solid. Remember, AQ means dissolved. So now we look at the 2nd compound, silver 1 bromide, and we'll look for the bromine ion. And the bromine ion might be the 3rd row down, if I remember correctly. So let's see, what does the bromine ion say? The bromine ion says that it can be soluble, right? But I believe it has exceptions. What are the exceptions for the bromine ion?
Ag plus Db plus 2. Hg 2 plus
So it says bromine can be, so it can form an aqueous solution, except when it's with one of these ions. And in this case, bromine is with silver. So since it's with the exception, it's not going to be soluble. So it's saying soluble except when it's with these. So since it's with silver, it's going to be insoluble. So I should write insoluble over here. And what insoluble means is it doesn't dissolve and we form a solid. So I'm going to put an S. And remember, this S doesn't mean soluble, this S means solid. So it's kind of, it's counterintuitive because when you say soluble, you want to write an S, but no, insoluble is S. Because insoluble means not dissolved, solid, precipitate formed. So this would be our precipitate, this would be our solid, the silver bromide.
So soluble is
AQ,
AQ.
yes, for aqueous. Yeah, I never quite do the tail on that. But. Right, now I'm going to write a word problem out that we're going to predict products on, because I know one of your homework does it in a word problem form, so I want you to know how to work something like that. So if we had sodium chloride and silver nitrate react to form which products? Include states of matter. Okay. So this is actually the same type of thing that we did here. It's just in a word problem form. So erase this to get us some room. So here they gave us the names of the two reactants. They say you take sodium chloride and silver nitrate, you react them. So these are our reactants. And then they're asking which products. So once again, we're given just the reactants and we're predicting the products. But they gave the reactants with words, so we have to figure out what these actually look like based off their names. So sodium, looking that up on the periodic table for its symbol, it's Na. But since it's an ionic compound, we need to look up the charges as well. Okay, so sodium's charge is alkali metal, so plus, anyone remember? +1, it's in group 1. And then it's with chlorine, because that's what chloride is, it's just the IDE version of chlorine. So Cl, the charge on chlorine is, I know it's going to be negative, but negative what? -1, it's a halogen. Okay, and we're reacting that, so we'll look at what that looks like in a second, with silver 1 nitrate. So actually, silver 1, I forgot that. So with silver's Ag, it's a transition metal. So that Roman numeral tells us the charge on it. And then nitrate, ATE. So that means it's a polyatomic, because it doesn't have that IDE ending. So we look up nitrate in the polyatomic table. We actually just had it in the last example. It was NO3, and it has a -1 charge. So this is going to help us figure out what the reactants look like. We look at the charges to figure out what the subscripts are going to be. For NaCl, they cancel, so we just need one of each. Same thing for silver nitrate. +1, -1, neutral. So I'm going to write the reactants up here to give myself some more room. So I have NaCl reacting with AgNO3. So my reactants are now written down, and I can predict which products. And the nice thing about this is I already have the charges And that's what I need to help predict the products. But what else might help me is knowing the type. What type of reaction is this? It's double, you're right. Yeah, it's a double replacement reaction because I have two compounds and they're going to switch partners. So knowing it's a double replacement reaction, it gives me that schematic of AB plus CD is going to give me AD plus CB. So if you can identify who's who, that'll help you switch it, right? So instead of using the pluses and minuses, let's try the schematic way this time. So AB, CD. So I know A and D need to be together. So A is the sodium. So let me get a different color. So A is my Na plus 1. I'm going to put the charges down here to help me figure out what the products look like. And then D is going to be the NO3. So the next product says that C and B should be together. So C is silver, and B is my chlorine. So I'm going to have my silver, which we said was a +1 over there, right? And my chlorine, which we discovered was a -1. Notice these ones work out nice as well with their charges. 1, 1, 1, 1. So we don't have to add any subscripts. The products will just be NaNO3 plus AgCl. And it's already going to be balanced as well with a 1, a 1, a 1, and a 1. So there's one of each element or ion. So it asks us which products, we got that, but it also says include states of matter. So double replacement reaction. This is the one where we have to predict if a solid forms, okay? And I said that the reactants are almost always aqueous. And you can prove that to yourself just by looking up these compounds on your solubility tables as well. So if you look up these compounds on your solubility tables, I think sodium is going to be the easiest one to find because it's in that very first row.
Yes.
And it says that it is soluble,
No.
no exceptions. So that means soluble or aqueous all the time. So if you're not sure, just use your solubility tables. So that would be an AQ. So when they're asking include states of matter, you need to put aqueous, solid, gas, whatever, one of those subscripts. So looking up the next one, I think NO3 is going to be the easiest one to find, because we looked that up last time as well. And that was in row 2, is that right? So it was soluble as well with no exceptions. So it's going to be aqueous. Just means that no matter what it's attached to, it's going to be aqueous. It's going to dissolve. So when we go and look at the products, the nice thing is we've looked up some of these ions already. So for my first product, sodium nitrate, we got that NO3 ion again, and we just said it's soluble no matter what it's attached to. So that means this one's going to be aqueous as well. So we just have one left to look for. So looking for silver chloride, you can try to find either of these ions, and I think chlorine's the first one you'll probably see. So looking at the chlorine ion, it says that it's soluble, or can be soluble, but there are exceptions for this one. So if it's with an exception, it's going to be insoluble. So what are the exceptions under that chlorine heading? I'm guessing silver's one of them?
Ag plus, AB 2 plus.
Okay, it's those same ones.
Yeah.
The HG.
2 plus 2.
Okay. So these are the exceptions, meaning if chlorine's with one of these, it's going to be insoluble, and chlorine it's with the silver. So insoluble means we're going to put an S here because it's a solid. So this would be the correct answer for this question. You would have to first start, figure out what the reactants look like. Knowing it's a double replacement would help you predict the products, and then go through and use your solubility tables to figure out the states. All right. Try another one. All right, so let's predict the products for this guy. In order to predict the products, very useful to know the type. And since we're only predicting products for these three types, that helps narrow it down a little bit. Okay?
It's combustion.
It is a combustion, right? So we know it's not synthesis or decomp just for the fact that that's not one of our choices. But hydrocarbon
Single.
with oxygen. Yeah, it's not single, it's not double. So the type, I'm going to put combustion. And so what you need to know about combustion is what are the products always, every time in a combustion reaction? CO2 and water. Every time. Okay, so if you know it's a combustion, those are your products. So predicting the products on this one's a little more straightforward. It's a memorization almost more than anything, because you don't have to switch partners. Because there's no ionic compounds here. These are all covalent. They're all nonmetals. So we don't have ions. They're sharing electrons. So balancing these, however, which is what we're going to do next, is a little bit more tricky. So to balance these ones, you can't really just go, oh, there's one of these, yep. You have to make a list on these. Especially since they, on the product side, we have oxygen in two different places. So it makes it even more difficult. So let's balance. To balance a bigger one, it's nice to make a list of all elements. So I have carbon, hydrogen, oxygen, and then start by writing how many you have currently. So to figure out how many you have, remember you're looking at the subscripts. So how many carbons on the reactant side? 4. How about hydrogens? 10. Oxygens? 2. Product side, how many carbons?
Oh,
There's just
one.
one, yep. So you're looking at the subscript after. If there's no subscript, it's just one. Hydrogens, 2. And then the oxygens are in 2 places. So I'm going to write how many in both those places and the total. Because that way I'll switch just one or the other as I'm adding coefficients. So there's 2 here, and then 1 here, for a total of 3. That way, if I put a 2 here, I'll just change this number and update my total. And that'll just kind of keep it a little less confusion there. So notice not balanced at all. What I prefer to do on these types is I leave oxygen for last, since it's in 2 places. So I go ahead and try to get my carbons and my hydrogens under control and hope that they just balance the oxygens for me. Okay, so we have 4 carbons on the reactant side, we need 4 on the product side. So I find carbon, it's here, so I need to add a coefficient. What coefficient is going to give me 4? 4, yeah, because we're doing coefficient times subscript. So 4 times 1, now I have 4. Hydrogens are next. 10 on the reactant side, I need 10 over here. So what coefficient can I put that will give me 10? So it's what times the subscript of 2 is going to equal 10. And you said 5, right? Yeah. So 5 times 2 Gives me 10. Now I skipped a step though, didn't I? I put coefficients, but I didn't update my oxygens yet. So let's do that and see how many oxygens we have now that we've done this. So this changed my carbons, but it also changed my oxygens. So 4 times 2 gives me 8 from that side. And now, how many oxygens in this water? Total. 5. Because 5 times the subscript of 1. So this changes to 13, right? So it didn't, there's no way that I can get 13 over here, right? Because this is a 2. No matter what number I put here, this is going to be even. And I have an odd number, okay? So what that means is my carbons and hydrogens, they're going to eventually change too. Because I'm going to have to add more oxygens on this side until I get an even number. But instead of just trying out numbers until I get even over here, what I'm going to do is stick with my plan and just worry about my carbons and hydrogens and wait until the oxygens balance. Or wait until they at least give me an even number. So to do that, I'm going to up this just by 1. Because I don't want to put 3 or 4, you always just go 1 higher, not ridiculous amounts higher. And what this is going to do is change my carbons. So now I have 2 times 4, 8 carbons, and 20 oxygens, or hydrogens, sorry. I'm looking at hydrogen, but saying oxygen. And then just try again. So let's balance my carbons. I need 8, so what number is going to go here? 8. It's not having me make the same mistake and do our oxygens as well. So 16, so that's 16 plus 5, 21. Let's do the hydrogens next. I have 20 over there, 10 on the product. So now what's this number going to change into to get 20 is my desired amount now? So what times the coefficient of 2 is going to give me 20? 10. So that changes this to 20. And it changes my oxygens to 10, right? So instead of 5 here, I have 10. So 16 plus 10, 26. I have an even number. So that means I can balance it now. I can balance out the oxygens. I have 26 on the product side. I need 26 over here. So we're going what times the subscript of 2 is going to equal 26? 13, right. And it should be an odd number, because if it was an even number, that means we could reduce it down. So whenever you're balancing, you should always have an odd number. You shouldn't be able to reduce it down any further. So this is now balanced, 2, 13, 8, 10. Combustion reactions, one of the hardest to balance for this reason. You just have to keep going back and forth. I did post a video for balancing that explains it a little different, or does it differently than I do. So if this isn't meshing with you, try watching that video, because they do it with like a common denominator fraction thing that doesn't work in my brain, so this is why I teach it this way. But if this isn't making sense, watch that video. Maybe that will help you balance easier. All right, let's continue though and keep trying some more of these predicting products examples. Yeah, we have time for at least one more. All right, let's do I almost wrote the products. Okay.
So we can use any different product photo for the balance?
You can use any what?
Like, for example, you got 13 oxygen, and over there is 13 total, or N26, right?
Oh, this is This was when we had a 5 there.
Okay,
So it's 26 now.
okay,
Yeah, because we have 16 from here, 8 times 2 is 16,
okay,
and then 10 times the 1
yeah,
gives me 10. So adding those two oxygens together gives me a total of 26. So I have 26 on this side, and then 13 times 2
yes,
gives me the 26. I just didn't finish writing it.
yes.
Yep. That's always good to double check at the end. Sometimes I skip that stuff. Makes for mistakes. Alright, so to figure that one out, let's figure out the reaction type for these three. Is it combustion reaction? No. Is it double replacement? Do I have two compounds? I have one compound, because a compound by definition is two or more elements combined, but the other one isn't a compound. Aluminum's an element by itself. So that tells me it's single. Because double replacement would have two compounds. Okay, so if you see an element by itself with a compound, it's single replacement. So to figure out what the products are going to be, we're doing the same thing we did for double. We're going to write each of these elements and what their charge would be. So why I say would be is because when aluminum's by itself, it's neutral. It doesn't have a charge. But we're going to write down here what charge it would have if it wasn't a compound. And to figure that out, we're looking at our periodic table. So aluminum is right under boron. It's in group 13. It's the only metal that's on that zigzag line. So since it's in group 13, it has 3 valence electrons, and it wants to get rid of all 3 to form +3. Since it's a metal, it's positive. So this charge is going to help us figure out who it's switching with, and it's also going to help us figure out what the new products look like, because new partners are going to have new subscripts based off of this charge. So the next step is to look at this manganese 4 oxide. So we need to figure out the charges. Manganese, it's a question mark. We don't know. It's a transition metal. We use its partner to figure out what its charge should be. So we have oxygen, but notice we have 2 of them. And so we need to figure out the charge on oxygen based off where it is on the periodic table. So it's in group 16. So what charge or what ion does oxygen form when it's in a compound? -2, because it gains 2 electrons to get its full octet. So if each of those have a -2, what's our total on the negative side? -4. So what does manganese have to be? +4, because there's only one of them. So that entire +4 charge is going to go on manganese. So now, to figure out the products, I need to make sure that on the product side, I have an element by itself and a new compound. And the new compound needs to have a cation and an anion together. So you're going to want the positive with a negative. So since aluminum's by itself on the reactant side, it's going to be partnered on the product side. And we're just figuring out who it's partnered with. Is it going to be partnered with manganese or with oxygen? If we partner it with manganese, we have 2 positives together.
Yeah.
That's not going to happen, right? The likes repel. They don't want to be together. It's opposites that attract. So aluminum's going to be with oxygen, because now we have a positive with a negative. And that's going to mean that manganese is going to be by itself. And when manganese is by itself, just like when aluminum was by itself, we don't write a charge on it. So for one of the final products, it's just Mn. That's it. We're not going to put a +4 because it only has a +4 when it's in a compound. Okay, so it's actually neutral when it's by itself. For the aluminum oxide compound, we figure that out using those charges. new subscripts. So that 3 for the crisscross method is going to become a subscript on the oxygen. The 2 is going to become a subscript on aluminum. So we need 2 aluminums and 3 oxygens. So Al2 plus O3, or not plus, sorry, I don't know why I wrote plus. Al2O3, there we go. Trying to move spaces so that we can balance. Now, since it's a single replacement, we're not predicting if solids forms or anything like that, okay? But we are still going to balance it. And this one might be a little more difficult to balance than most single replacement reactions. So I'm going to erase those pluses and minuses so that we can write our list. Actually, I'll just write it down here. Maybe there's room. So anyone still needs that? So we have aluminum, manganese, oxygen, aluminum, manganese, oxygen. Let's write how many we have of each. So this is the balancing part. Aluminum is just 1, manganese, oxygen, got the subscript, 2. Product side, aluminum, how many?